All right, let's check if we're live. Are we live? Are we live? Are we? Are we live? Are we live? Let me post the link. 1, 2, 3. I don't hear anything. What's going on? Why can't I hear anything? No audio. There's the reason. Okay, now I can hear it. No audio. Very, very nice. We very nice. Let's see notifications. Right. Okay. All right. So let's go to the YouTube. Here's the YouTube. I invited some people to Discord. So far, no one is showing up. Let me close some windows. You know what? I think this is done. He usually takes down the stream, but maybe there's a little bit left over.
So that's what's going on.
Yeah. He kills the stream. So he says the reason is why does he say? Because he used to say it's because they will take him down. But then he says, you got to pay me. So you got to pay me. You got to pay me money to have access to the stream. And then a week, but he never posts it on YouTube in the long run. But on Rumble, it's always available a week later. Anyway, so we can Lagrangian. Let's see this. Maybe we should listen to a little bit of the Lagrangian. 1 second. I have a message. Oh, spaghetti. Hey, let's continue talking. Please. I really enjoyed our convo yesterday. I'd like to ask him if he has other people that are like him that know so much physics. Let's see. I want to close some windows. Okay, this we can close. So do I still have the link? That's StreamYard. Maybe later. This is my StreamYard. So if you join, we can look at YouTube together. Anyway, do you know anyone else like you who might be interested in talking to me? Do you guys have a Discord server? Okay, I'm thinking maybe we should go back to this Lagrange, because I do want to figure out the Lagrange method. Okay. So I'm just thinking. Yeah, maybe we should listen a little bit more to the Lagrange, to the boring Lagrange. Okay.
So Newton told us to start by writing the total force and setting it equal to ma. Lagrange instead tells us to start by writing Lagrangian like we have here, and then using it to write what's called the Euler-Lagrange equation. That's d by dt of dl by d theta dot equals d.
So Lagrange taught us to write the Lagrangian and then the Euler-Lagrange.
L by d theta.
And the Euler-Lagrange just finds the least action, basically. where the Euler-Lagrange is true, that's the least action.
By the way, the curly B's here stand for partial derivatives. If you've never seen those before, don't worry about it. For practical purposes, they behave just like ordinary derivatives. Now, I'm not going to get into too much motivation as to where this Euler-Lagrange equation comes from in this video. What I just want to do for now is write it down and investigate the consequences. But the short answer is that the Euler-Lagrange equation is the condition for the action S to be minimized, where the action is defined as the integral of the Lagrangian. The claim is that of all the possible paths that a particle could follow, the one it actually chooses is the path it minimizes, or more precisely extremizes, the action. This is known as the principle of least action, and the implication is that the trajectory satisfies the Euler-Lagrange equation. But unpacking all of those details would really require its own dedicated video. Right now, I just want to see what happens when we plug the pendulum Lagrangian into this Euler-Lagrange equation. The right-hand side of the Euler-Lagrange equation is the derivative of L with respect to theta, and we're going to treat theta and theta dot as independent variables when we take these derivatives. That means that but unpacking all of those details would really require its own dedicated video. Right now, I just want to see what happens when we plug the pendulum Lagrangian into this Euler-Lagrange equation. The right-hand side of the Euler-Lagrange equation is the derivative of L with respect to theta, and we're going to treat theta and theta
Okay,
dot as
so the
independent
right hand is dl d theta.
variables when we take these derivatives. That means that the only contribution to dl by d theta comes from the cosine theta term in the Lagrangian, and we get dl by d theta equals minus mgl sine theta. For the left-hand side, we need to know what dl by
So this is L. So dl d theta. This is theta dot. We don't care. This is theta. So it's mgl, I guess, sine theta, or negative mgl sine theta, because the derivative of cosine is negative sine, I guess. Okay. And now we're going to do dl d theta dot, which is going to be 1/2 ml squared times 2. All right, the 2 comes down, and we have this times, I don't remember, how do you do a derivative? So the 2 comes down, and this goes down by 1, but then we need to also take the derivative of theta dot with respect to theta, which gives us d theta dot d theta. Let's see what he says. I don't know. I mean, is theta an independent variable? No, time is the independent variable. Theta is a function of time. So, but we're taking a derivative with respect to theta.
by d theta dot is. And from the kinetic energy term, we get ml squared theta dot. Then take
Oh, that's it? Just ml squared theta dot? Oh, because it's with respect to theta dot. So there's nothing else. That's perfect.
d by dt of that just turns theta dot into theta double dot.
And d dt of that is, yeah, ml squared theta double dot, I guess.
By the way, the L by d theta dot here is called the momentum p corresponding to the coordinate theta.
What is?
The L by d theta is called the generalized force.
This is the momentum? Look, L theta dot is velocity. ML is the inertia. So you could say this is MV. So it's P. But I wish you would develop it. I mean, how exactly do you get P? That's I'm assuming. It makes sense. And what is this? This is tau or F? What did he say this is?
By the way, the L by d theta dot here is called the momentum p corresponding to the coordinate theta. The L by d theta is called the generalized force. The reason for the terminology.
The generalized force. So why is it generalized force? So sine theta, which is sine theta? Which is theta? I'm trying to think what direction. So mgl is just, mg is the weight, and L theta, it doesn't matter. Sine theta is theta when it's small angles, which I think we're assuming here. Either way, L theta is again, what is L theta? That's just the arm. That's R. No, L is R. L is the arm. What do you get from the arm times theta? I don't know. So anyway, this is just a component the component. This is mg. Mg is the weight, and L theta. I mean, mgl is the arm. That's the torque. I don't know. I wish he would explain what he means by these things.
Analogy is that the Euler-Lagrange equation is then reminiscent of Newton's second law. Force is the rate of change of momentum.
Oh. So this is the generalized momentum, and this is the generalized force. So this is the change over time in momentum is the force, which is force equals dp dt. But why is this force? This is the change of the Lagrangian over theta. Okay. Interesting. Very interesting how these things fit together. Oh my god. Let me turn this off. Okay, what do we got? We're all alone on the Discord. Okay. And of course, no one is listening. It's fine. It's fine.
So the result of plugging in our pendulum Lagrangian into the Euler-Lagrange equation says that ml squared theta double dot equals minus mgl sine theta. Canceling out the common factors.
So what are we saying? So we're saying that the Euler-Lagrange is ml squared double dot is the left side, and negative mgl sine theta is the right side. Okay.
We once again obtain theta double dot equals minus g over L sine theta. The same equation of motion we obtained earlier.
So ml drops out from both sides. So we're left with theta double dot and g over L and sine theta. Okay, and negative. Okay.
F equals ma. But this time we got it using a very different strategy based on.
So this is some sort of acceleration, angular acceleration, and this is somehow the force, g over L. This is just acceleration. This is pure angular acceleration. So you could have L theta double dot, that's actual acceleration, and it's related to g. So from, what do you call it? Dimensional analysis. You always have to make sure the dimensions are correct. So L theta double dot is acceleration, meters per second squared, and g is meters per second squared. And sine theta is a scalar, so it's fine. It's dimensionless, so it's fine. So the dimensional analysis ends up being correct.
On the Lagrangian and the Euler-Lagrange equation. All that might seem a little bit abstract if you've never encountered a Lagrangian before, but in fact, it's a very useful way of quickly getting at the equations of motion for a system, oftentimes easier than using F equals ma. If I'm faced with most any mechanics problem, I'll usually start by writing down the Lagrangian. For one thing, we don't have to deal with any of the annoying vectors that show up in F equals ma. We can just choose whatever coordinates we like to describe our system, including potentially non-inertial coordinates, write down the Lagrangian, and then write the Euler-Lagrange equation for each of the coordinates. The Lagrangian formalism also makes it much easier to deal with constraints and to understand symmetries, but those topics will have to wait for another day. Now, if you really want to master these ideas, you've got to solve problems for yourself. So I posted a problem sheet down below where you can apply the Lagrangian method to a challenging system. It's our pendulum again, this time in the guise of a pocket watch with magical powers. And now the pivot is being shaken back and forth by a mysterious hypnotist that you bump into at the town fair. So you should definitely go work that problem out to test and deepen your understanding. And I've also posted a link to the solutions, which are available on my website.
Wait, what?
For each of the coordinates. The Lagrangian formalism also makes it much easier to deal with constraints and to understand symmetries, but those topics will have to wait for another day. Now, if you really want to master these ideas, you've got to solve problems for yourself. So I posted a problem sheet down below where you can apply the Lagrangian method to a challenging system.
This is good, but does he have answers?
It's our pendulum again, this time in the guise of a pocket watch with magical powers. And now the pivot is being shaken back and forth by a mysterious hypnotist that you bump into at the town fair. So you should definitely go work that problem out to test
the pivot
and deepen your understanding.
So this is moving back and forth. Something is moving back and forth. So there's x naught at t. So this is moving back and forth, I guess, and the pendulum is Swinging. Miss Madeline.
And I've also posted a link to the solutions which are available on my website. Finally, let's look at the pendulum using Hamiltonian mechanics. This time, instead of starting with the Lagrangian k minus u, let's write down the total energy k plus u. For the pendulum, we get 1/2 ml squared theta dot squared minus mgl cosine theta. That minus sign is again there.
So energy is equal to. Wait, this is the Hamiltonian? So did he skip to the Hamiltonian? Lagrangian and Hamiltonian mechanics in on 20 minutes problem sheet. If you notice any errors in this file, please let me know at feedback physics with Elliot. You can just have a Google Docs document and allow anyone to write comments. Solutions available at blah blah blah. Oh, there is solutions. One summer's night, you are strolling around a carnival that has been set up in your town for the weekend when you pass by a booth with a sign that reads Miss Madeline's Mind Mystifying Palace. Miss Madeline herself is standing next to it and she explains. Okay. Mhm.
Finally, let's look at the pendulum using Hamiltonian mechanics. This time, instead of starting with the Lagrangian k minus u, let's write down the total energy k plus u. For the pendulum, we get 1/2 ml squared theta dot squared.
So Hamiltonian just means the energy. That's the Hamiltonian. I don't get it. Why do you? So I don't get it.
Minus mgl cosine theta. That minus sign is again there because the potential is negative. Now remember that we defined the momentum p by ml squared theta dot.
So 1/2 ml squared theta dot squared. I mean, we already worked out k and u, so now we're just adding them, and it happens to be a negative sign here.
I'm going to use that expression to rewrite the first term in the energy as p squared over 2ml squared. That means we can write the total energy in terms of theta and p into u. For the pendulum, we get 1/2 ml squared theta dot squared minus mgl cosine theta. That minus sign is again there because the potential is negative. Now remember that we defined the momentum p by ml squared theta dot. I'm going to use that
So we defined the generalized momentum.
expression to rewrite the first term in the energy.
So it's ml squared theta dot. So L theta dot is the velocity. L theta dot is just the velocity. So that's mv, but there's another L. So it's mvl. I don't get it. Right? Well, what am I missing? It's right. Momentum is mv, but L theta dot is already v. There's an extra L here. Momentum. What is momentum? Is momentum is the same units as force? No. Force is newtons, and it's equal to dp dt. So it's change. Force is newton, and dp dt should also be newton. But it's something divided by time. So force is newton. Oh, F equals ma. No. Before we get to ma. Oh, wait, 1 second. It's the change in mv, the change in p. So p is the same as mv. It's mass. P is the same units as mass times velocity. So it's gram meter per second. So p is gram meter per second. Gram meter per second. I don't get it. The units, dimensional analysis doesn't work. I'm supposed to get grams meters per second. So d theta dt is angle per second. L theta dot is meter per second. So all we need now is the mass, but this cannot be momentum. Dimensionally, it cannot be momentum.
P squared over 2ml squared. That means
What am I missing? Hmm. Um. Oh, someone is watching. Anyway, as a physics freshman, I recall reading the terms. Anyway, Newtonian. Okay. My question is, why do you call this P? This is not P dimensionally speaking. This is energy. Energy is force, which is change in momentum times distance. So we're multiplying by distance. So mv, this is mv l. mvl, this is kinetic energy. I don't get it. I don't know what he's doing. I mean, he's not clear. Anyway, he's just defining it. We'll just go with the definition. P is just defined as ml square theta dot, fine. So ml square theta dot, here's ml square theta dot. There's another theta, an extra theta dot here, because it's squared, and a 1/2. 1/2. All right, so this is the 1/2. So again, ml squared theta dot, ml squared theta dot. So we're multiplying, so we have P times 1/2, or theta dot over 2. So here he's doing P, he's saying this is P squared, which is m squared L to the 4th theta dot squared. But he's removing 1m, the 1l squared. So P squared, I need to write this down somehow, is P squared. There is an m squared, but he's removing 1m. There is an L to the 4th, but he's removing an L squared. So it's L squared, so ml squared. And there is a theta dot squared. So there's a theta dot squared in here, and it's divided by 2. And here's the theta dot squared divided by 2. So that's fine. So he's representing it, he's writing it out as that. Okay.
That means we can write the total energy in terms of theta and P as P squared over 2ml squared minus mgl cosine theta.
Yes. So the total energy is P squared over 2 ml squared minus mgl cosine theta. Fine.
Quantity is called the Hamiltonian, and it's the starting point for Hamiltonian mechanics, just as the Lagrangian was the starting point for Lagrangian mechanics. Whereas we use the Lagrangian to write down the Euler-Lagrange equation, we'll use the Hamiltonian to write Hamilton's equations, which say that theta dot equals the derivative of h with respect to...
Oh, so Hamilton has his, like the Euler is the equivalent of the Euler-Lagrange.
As we use the Lagrangian to write down the Euler-Lagrange equation, we'll use the Hamiltonian to write Hamilton's equations, which say that theta dot...
Oh, so Hamilton has an equation besides defining the Hamiltonian as the total energy. Besides that, he has the Hamiltonian equation.
equals the derivative of h with respect to p, while p dot is equal to minus the derivative of h with respect to theta. Note that whereas f equals ma in the Euler-Lagrange equation gave us a single second-order differential equation, Hamilton gives us a pair of first-order equations for theta and p. By the way, it's important to mention here that while the Hamiltonian was just the total energy in this simple example, that's not always necessarily the case. So let me give you the completely general definition before we move on. Remember that the momentum p was defined...
Okay, let's again listen to this. Yeah, I'm going to lower the speed because I really need to understand this.
Which say that theta dot equals the derivative of h with respect to p, while p dot is equal to minus the derivative of h with respect to theta.
Mm-hmm. So I don't know what the general form. This is a very specific problem. I don't know what the general form would look like. But theta dot, I guess is theta the independent variable or is t? I don't see t there for now. So I guess theta is the independent. So theta dot is the HDP, the change of the Hamiltonian, the total energy relative to changing just the generalized momentum or something. And the change in the generalized momentum is the negative change in the Hamiltonian, the total energy relative to the angle theta. All right.
Note that whereas f equals ma in the Euler-Lagrange equation gave us a single second-order differential equation, Hamilton gives us a pair of first-order equations for theta and p.
Okay, these are first order. This is first order differential equation. Okay. Again.
Hamilton gives us a pair of first-order equations for theta and p.
So Euler-Lagrange is one equation of second order. This is two equations of first order. Okay.
By the way, it's important to mention here that while the Hamiltonian was just the total energy in this simple example, that's not always necessarily the case. So let me give you the completely general definition before we move on. Remember that the momentum p was defined as the derivative of L with respect to the velocity. The Hamiltonian is defined by taking p times the velocity and then subtracting L. And then as before, you replace all the theta dots with p's.
What? I mean, where does all this come from? So P is dl d theta dot. This is from the Lagrangian. And H is P theta dot minus L. And theta dot what?
Now that may look like it comes out of left field.
Yeah, exactly.
I don't have time to explain it right now, but you can check that this definition reproduces the total energy in our pendulum example. But in the system I ask you to solve on the problem sheet, you're going to need this more general definition.
So let's see what we get for our simple pendulum. The derivative
Okay, we'll just ignore that and let's just go with these. Given these two first order equations, so we need to do the h dp and the h d theta. I mean, theta dot equals the h dp and p dot equals negative the h d theta.
of h with respect to p is just
So the h dp, there is p, so it's 2 times p over 2ml squared.
p over ml squared from the first term. For the
derivative negative dh over d theta, so I think it's positive mgl sine theta, and that's it.
with respect to theta, we get minus sine theta from the derivative of cosine
So it's positive mgl sine theta.
times two more minus signs gives us an overall minus mgl sine theta.
There's a minus. So 1 second. So there's this minus, meaning when you take a derivative of cosine, it becomes negative sine. Is that the one? And this becomes positive, but this says negative. Okay.
Theta. So Hamilton's equations tell us that P equals ml squared theta dot.
Okay. So P is equal ml squared theta dot, yes.
And P dot is equal to minus mgl sine theta.
P dot, yes, is negative mgl sine theta.
This first equation is just the definition of momentum again. If I take its rate of
It's not momentum, because L theta dot is V. So it's MVL. It's not exact. The units are wrong.
Change, it says that P dot equals ML squared theta double dot.
Okay, let's see. So it's ML squared theta double dot. Yes. This dot, if you want to add another dot, right, these are constants, so we don't care. So it's just theta dot becomes theta double dot. Yes.
Now, if I insert that into Hamilton's second equation, we learn that
ML squared theta double dot equals negative MGL sine
ML
theta.
squared theta double dot is equal to minus MGL sine theta. Crossing out the common factors, we arrive.
So M drop out, L drops out. So again, we have theta double dot equals negative, M is gone, it's just G over L sine
Arrive
theta.
one more time at our old friend, theta double dot equals minus G over L sine theta. So Hamilton's equations are equivalent to the original equation of motion that we got either from
Okay, that we expected. All three methods give us the same result.
F equals ma.
But what does Hamilton actually say about reality? I mean, Lagrange is the least action. What is Hamilton's principle?
Or from the Euler-Lagrange equation. They just split the single second-order differential equation into a pair of first-order equations. First order because we only have one derivative acting on theta and p. But what does that really buy us? Hamilton's pair of first-order equations aren't necessarily any easier to solve than the single second-order equation of motion that we started with. What we do gain, however, is a new geometric perspective on the mechanics of the pendulum by connecting it to what's known as a flow on phase space, as I'll now explain. To specify what the pendulum is doing at any given instant in time, we just need to give its position and velocity, or equivalently its position and momentum, theta and p. With this initial data, we can figure out what the pendulum will be doing at any later time by solving Hamilton's equations for theta of t and p of t. The pairs of thetas and p's define a plane which is called the phase space of the system. We start out at our initial condition, theta of 0, p of 0, and as time goes on, our coordinate moves around this theta p plane, tracing out a curve which is known as a flow on this phase space.
You could have a three-dimensional shape where you start with t, and t is the independent variable that causes changes to theta. I mean, you could just show how this thing evolves in time, because this way you can't really see how it evolves in time. It's difficult unless you say that the path, the arc length, the trace itself is time, but it's easy to just add a dimension.
These flows are very special. They won't just travel along any old curve in the theta p plane. In particular, because the energy of the pendulum is conserved, if we evaluate the Hamiltonian at any time t along the flow, we're guaranteed to always get the same number. The energy is a constant of the flow. Here's what a few of the lines of constant energy look like for our pendulum. Because the energy of the pendulum is constant, we know that our initial point has got to move along one of these lines of constant energy as it evolves with time. So here's another little animation that I made. Again, you drag these sliders to set the initial conditions that you want for the pendulum. The initial conditions pick out your starting point in the phase space. So here I'm starting out with some particular angle and 0 momentum. Then we're going to let the pendulum go and see how it evolves with time.
1 second, let me see. So theta 0 is 2.38, I guess, radians? But this looks like this is theta, so you drag theta out to here, and omega 0 is 0. Okay, so omega, oh, this is omega, this is not p.
As the pendulum moves, its angle and angular velocity are changing with time, and therefore the phase space coordinate is changing.
Notice that these are not functions. This space, these are not functions. But if you had time, if you add another dimension, time, you could have a function. Yeah, for each t, you would have a unique theta and then a unique, I don't know.
But since the energy is constant, we know that the particle has got to travel along this line of constant energy. So again, I'll put a link to this little
So if these are lines, you could look at these lines as a topology, meaning is it called a topology? The height. It's like a map. It's a mountain map. It tells you the height. This could be viewed like a mountain, and you're just traveling on a mountain or something. Oh my god. Oh my god. Come on. Anyway, I had a date last night, and it was very nice. I really enjoyed the date. I was very upset because in the beginning she was like, "Let's meet there," and then we ended up. I said, "No, I want to pick you up," and she said, "Fine, you're cute. Pick me up." And of course, the first thing I do when I pick up a chick is I ask permission to put my hand on her lap and grab her thigh and hold her hand. So obviously that makes it romantic instead of just friendly. So it was beautiful. Then we ended up walking by the anyway, I can't tell you anything about the topology of where we went because then you would be able to trace me to where I'm at. So anyway, we had a beautiful walk. The weather was, I can't say anything about the weather, but it was okay. Yeah, but she's very difficult to get. Anyway, so I'm wondering, like, I'd like to have more ways to see this. I'd like to see this in more dimensions, different dimensions. He said this is p, but now it's omega. What is omega? I don't even know what omega is. Omega is usually the velocity of theta. So I guess it's related to, this is basically theta dot. Okay.
animation down below so that you can go play with it for yourself. Notice in particular that there are these two different kinds of curves of constant energy. We've got these closed loops near the center of the phase space and these open wavy lines farther away. Try setting the initial conditions so that the particle sits on one of the wavy lines and figure out what the physical difference is between these two types of phase space flows.
So what would happen in one of these waves? Like this one closes, but this one doesn't close. So this is a higher omega. So you can have a very small theta. Right? Because here we started with omega equals 0, but we can start with omega, with this omega, and get the same. We would still get this. This is a sine shape. Sine. This is already no longer a sine, I think, because theta is too big. Yeah, I mean, even this is not sine. This is becoming a non-circle. Very small is circle, but as the theta becomes bigger and bigger, you lose your circularity until something happens. And this is already, what is, So theta. So here you cannot, what it says here you can start with theta while omega is 0. But here you can no longer start with theta and omega is 0. There's no such option. If you start with any theta here, you have to be here. This is like undefined or something. I guess it's defined, we just can't see it well. So what happens when you get to here? Let's start this way. So you can start at theta equals 0, but with a certain omega, a faster omega, faster omega, faster, faster. And then what happens? I don't know.
All this is only the tip of the iceberg for Lagrangian and Hamiltonian mechanics. And I'm really hoping that I've whet your appetite to make you curious to go off and learn more for yourself. Not only are these fascinating and extremely useful approaches to classical mechanics,
So what I discovered is that by looking at topological maps and graphs teach me the most. I learn by far the most, or animations. The most I can learn from animation. When you take a mathematical equation and you graph it or turn it into an animation, that's when I begin to understand. And the more I dive into an animation or a graph, the more I understand, the deeper my understanding is. Like when I studied economics, it was when I started drawing these 3D maps that I began to really understand economics. And then I went to my professor and I told him, listen, did you know that instead of like talking to us and showing us mathematical equations, you can actually draw it like it here is a calculator, a graphical calculator that turns an equation into a graph. Then you can just take a look at it, then you can see everything. That like one picture tells you everything. His response was, yeah, I never understood that. It's like I was like, wait, what is going on? And this guy was a genius. I mean, he was able to develop these equations, these partial derivative and integrals, and it was so amazing. It was so beautiful. But the most beauty is when you drew it in a graphical calculator. And that was beyond his ability to understand. I don't know. Really weird. Really, really weird. So it's like different people have maybe different brains or something. Who knows? Who knows? I don't know. Okay. But so I'm always looking to see animations, but like with this animation, he ends up not explaining it. Where is he? So he ends up not explaining it. He's just asking. Is there a link? Did he say that he has a link to this animation? But this really has, I would say, has nothing to do face space. Amazing.
a constant of the flow. Here's what a few of the lines of constant energy look like for our pendulum. Because the energy of the pendulum is constant, we know that our initial point has got to move along one of.
So this is like a topological map that you could say that this is this low energy and this is a higher energy. This is like omega is faster. So this system is higher. So this is like a low point, and this is the bottom. So you could look at this could be viewed from the top as a bowl, like a bowl of soup that's empty. So this is the lowest energy. This is a higher energy. How do I know this is a higher energy? Because it's moving. We have a certain omega when it gets to theta equals 0. But here there is a higher speed, higher omega when it gets to theta equals 0. So this is a higher energy system, and even a higher energy system, and a higher and very high energy system. And it basically comes to a full stop here. And after that, the system rotates in only one direction. This is what it means. So theta only moves in one direction forever. So what happens here? Well, let's think about it. This is high energy. After that, it starts spinning clockwise, let's say, and this is already spinning counterclockwise. So when it's spinning clockwise, but it comes to almost a stationary point at the top, right? At this point, omega, I'm sorry, it, okay, let's see, we have a message from Sinos. Busy today, okay. Anyway, so the Hamiltonian is phase space. So when people talk about phase space, that's what they mean. So phase space is actually a very useful diagram. So I've heard people use this term and I never knew really what it meant. It's like, what do you mean by phase space? I don't know why this is phase space. What? Okay, so this is, right, I'm just wondering what happens here. So you start from a certain omega and you let it go and it rotates clockwise. I guess this would go up and down, up and down, up and down. Now it makes sense. Okay. So this is just this theta, right? So this is theta equals 0. He didn't say the values. So this is probably theta equals 90 degrees. Theta equals 0. That's at the bottom. And this is theta at 90 degrees. So when you let go, it could go this way or this way. So if it goes this way, it rotates. So omega is positive. If you let go this way, so omega is positive. So let's say it's rotating clockwise. No, omega is negative actually. The convention is that it's right-hand rule, I guess. It's counterclockwise when we look at the top. So we're looking at the pendulum and omega, the way we define theta. So omega is counterclockwise. So theta, right? So theta is at the very top. We're letting it go. And theta moves to 0. As theta moves to 0, this is maximum omega. And then theta goes all the way to the other side, tippy top, and back again. Okay, but if we go here, there's no such thing. Because this theta is already over here. This is the maximum theta. There's no, oh, so it gets cut off. There's no point beyond this point. So whenever theta gets to here, we continue over here. So phase space is like a Pac-Man game board that you leave on the right, you continue on the left. Mm-hmm. So that's why there's no point here. This point is this point. So that's useless. So there's no point in discussing anything beyond. So what does it mean to start? Okay, so this is at the tippy top. You let go. Or you can start at the tippy top and push it, give it a push. Let's say you push it positive omega. Oh, this is positive omega. So it's pushing, you're pushing it counterclockwise from the tippy top. And you're pushing it. And as theta becomes smaller, it's accelerating until it stops accelerating. At the maximum omega, at the bottom, theta is 0. And then it goes to the tippy top again at a certain omega, and it continues over here. So it must always follow this trajectory from left to right. Right? Well, positive omega means you're giving it a kick. Now, it doesn't matter if you read it from left to right or you read it from right to left. So you could say, I give it a kick. I'm kicking it. It doesn't matter now if you say it does this or from here, it does this. Or does it? I mean, this location is different than this location. This is theta to the left all the way to the top. This point is identical to this point. Anyway, this is really, really complicated to think about. But once you let it run, then you map it to your brain. So let's see what
These lines of constant energy as it
where can we play with it?
evolves with time. So here's another little animation that I made. Again, you drag these sliders to set the initial conditions that you want for the pendulum. The initial conditions pick out your
Where can we play with this? Take the full course Lagrangian mechanics. I guess it's a paid course. The problem set. Where is the animation? How do you play? There's a little, mm, mm, where is the and the animation. Okay, let's see if we can find the animation. This animation. So let's see that it works. Okay. Reset, start. Very nice. Reset. Oh, that's good. So we can move theta anywhere we want and omega anywhere we want. Fantastic. Just as I expected. Amazing. This is... What is it gonna do? I think we said it's gonna move to the left, but there's no difference. Um, hmm. It moves to the right, but it's counterclockwise. Oh, I cannot drag it. Hmm. Simple pendulum with phase space flow. So obviously this is a high energy system. So this is, oops, I cannot drag it. So we can have a zero energy system. Is it going to let me do zero energy? It's not letting me do zero energy from point 1 to point 3. It's not letting me do zero energy. But you can see that it's moving very slowly. This is a very low energy system. It's swinging very, very slowly. Notice that the time of the swinging should not be influenced. Let's start from, okay. For small swings, it should take the same time. But does it? Does it take is the period of the pendulum constant? It should be, right? I mean, obviously it's not. This we cannot touch. I mean, it is reacting as if we should be able to move it, but how did he okay, drag this. Okay, I think we figured everything out that we could figure out. What's the physical difference between them? Anyway, how did he do this animation? What is running this animation? Courses. Tensor calculus. That's what I need to study. Tensor calculus is a clear and accessible in a clear. Okay, tensor. Basically. Basically. 3 parts. Dr. Elliot Schneider. I've been studying physics for about 2 decades. Harvard. Caltech. Why tensors? For quantum field theory, you need tensors? That's terrible. Wait, time for our next. That's a tensor? Thus, the inertia tensor yields the angular momentum. Inertia is a tensor? I don't know. Oh my god. A rank. Learned the true form of electromagnetism. But there's no tensors. In the language of tensors, Maxwell's equations boil down to essentially one line? I don't believe it. You can write all of Maxwell's in one line using tensors? How? How is that possible? This is just intro students who find my teaching helpful. Cartesian. So this is like an hour. Curvilinear tensor fundamentals. Space-time. So each part has like 10 videos. Minkowski. One-to-one coaching support. Coaching. Wouldn't be possible for me to give detailed question and answer support to everyone, though I do my best. Closed. Look at the price. So tensor calculus, 3-part bundle, $498. 3-part bundle plus coaching pre-order, $897, and it's closed. He's not even taking in. So you can part 1 Cartesian, part 2, part 3. And it's closed. Wow. But what is it? How many hours is each part? Wow. Fascinating. What's the size of his channel? 165,000. Fascinating. I'm a little bit hungry. Even though I just ate, but I'm hungry again. Okay, what do we got?
Your starting point in the phase space. So here I'm starting out with some particular angle and zero momentum. Then we're going to let the pendulum go and see how it evolves with time. As the pendulum moves, its angle and angular velocity are changing with time, and therefore the phase space coordinate is changing. But since the energy is constant, we know that the particle has got to travel along this line of constant energy. So again, I'll put a link to this little animation.
What I would do is I would build a 3D shape where with lines like a topology, but this would be a rail and it would actually go up and down so that it would slow down here and speed up here. This should be speed up here and slow down here. This is 0 speed.
Down below so that you can go play with it for yourself. Notice in particular that there are these two different kinds of curves of constant energy. We've got these.
Is the speed 0 over here? It says that the speed is 0, but it doesn't look like the speed is 0. It doesn't stop over here. But omega should be 0 here. Is it? Is this the top?
Closed loops near the center of the phase space and these open wavy lines farther.
So the speed is actually 0 over here. The omega is 0 over here, but it's barely noted. You cannot tell. It looks like it's flying right through. It's moving through, but omega is 0 as it's moving through this. It's not like the omega is non-zero here. The omega is 0 throughout this region. I mean, it's only 0 exactly at one point. This is fascinating. I can imagine so many ways of demonstrating this using animations to simplify, to analyze it. Wow, amazing.
Away. Try setting the initial conditions so that the particle sits on one of the wavy lines and figure out what the physical difference is between these two types of phase space flows. All this is only the tip of the iceberg for Lagrangian and Hamiltonian mechanics, and I'm really hoping that I've whet your appetite to make you curious to go off and learn more for yourself. Not only are these fascinating and extremely useful approaches
I wonder why he closed the registration.
to classical mechanics, they're also fundamental to the way we think about quantum mechanics. For example, functions on phase space in classical mechanics turn into operators on the quantum space of states in quantum mechanics. And if you know the state of a quantum system at t equals 0, the Schrödinger equation says that the state at a later time t will be e to the minus I over h bar, h times t, acting on the state, where h is the operator version of the classical Hamiltonian function. So if you keep studying physics, I guarantee you'll see Lagrangians and Hamiltonians popping up all over the place.
All right, that's it for this video. I really hope you found it interesting. You can find all the links down in the description, to the notes that I posted on my website, to those animations, and to the problem sheet and solutions. Please hit the like button, subscribe to the channel to see more physics videos very soon, and also leave me a comment to tell me what topics you might like to see me cover in the future.
I mean, definitely thank you. Amazing. Now let's see, explaining the principle of least action.
Hello and welcome everybody. My name is Elliot, and in this physics mini lesson, I'm going to tell you about one of the most profound and far-reaching ideas in physics. It's called the principle of least action, and it's a different way of looking at physics that underlies a huge amount of what we humans have learned about the world in the last few hundred years, from Newtonian mechanics to relativity to quantum mechanics and quantum field theory. The basic idea goes like this. Say we have a particle that's traveling from point A to point B. What path is it going to follow to get there? Newton gave us one way of answering that question. But in the 17 and 1800s, Lagrange and Hamilton and others came up with a different proposal. They assigned a number to each possible path called the action, and they showed that the trajectory the particle follows is the one for which the action is minimized. Actually, in quantum mechanics, Feynman showed.
So he has a bunch of books here, but he doesn't have book holders. So this book in time is going to get deformed. It's worth it to invest in a book, like in a book holder. Like 2 book holders would be a good idea. What do not, I don't know. What is this? Oh, it's a lobster. Oh, shoot. Okay, 1 second, I'll be right back. Okay, I'm a little bit hungry, so maybe we should stop here. Let me just check. Wait, should be able to hear myself, no? Yeah, I'm able to hear myself. Let me check here. Good. This microphone is the best. This headset is just the best. Let me see any notification. This microphone is the best. I want to hear myself. Let me just see if I have any interesting notification. Oh, Tash Peterson. Farmer warns vegans stay away from my livestock. 8 years of sadistic. Very interesting. Okay, I'm gonna go eat. How long has this been? Oh, just over an hour. Okay, see you. Let me get out of this and see you later.